Welcome to the podcast. Today we're diving into the fascinating world of Cutlass, a high-performance library developed by NVIDIA for CUDA programming, particularly focusing on matrix operations. With its latest release, Cutlass 3.8, there's a lot to unpack, so let's get started. Cutlass stands for CUDA Templates for Linear Algebra Subroutines and Solvers. Quite a mouthful, isn't it? But what it really aims to do is make it easier to perform matrix-matrix multiplication, or GEM, essentially crunching numbers at incredible speeds. This library provides modular components that allow developers to pick and choose different ways of parallelizing their computations, tailored specifically to modern NVIDIA architectures. So what's new in Cutlass 3.8? We've heard it supports NVIDIA's latest Blackwell architecture. What's the big deal about that? Great question. This new version integrates the 5th-generation Tensor Core instructions, making use of the latest advancements to get optimal performance. These Tensor Cores are like supercharged engines for computational tasks, allowing massive parallel processing. It's similar to how upgrading your car engine can take your whole machine to the next level. It sounds pretty technical. Can you explain in simple terms what those Tensor Cores do? Absolutely. Think of a tensor core as a specialized worker in a factory that can handle multiple tasks at the same time. Traditional processors might do one thing at a time, but tensor cores allow for simultaneous processing of floating-point operations, which drastically speeds up tasks like machine learning and data processing. This makes them perfect for applications requiring heavy computations. Moving on, Cutlass 3.8 also introduces enhanced support for mixed precision computations, meaning it can work with different types of numbers simultaneously, like combining half-precision and single-precision floats. This flexibility gives developers the ability to maximize performance while managing memory usage more efficiently. They must have done a lot of work to support so many data types, right? Exactly. Cutlass is built to handle various data formats from traditional FP32 and FP16 to the more niche E4M3 and E5M2 formats, which are specifically optimized for certain calculations. This means developers can fine-tune their applications based on the requirements of their workloads. Now let's talk about performance. In the world of computational libraries, efficiency is key. Cutlass is designed to extract maximum performance out of NVIDIA GPUs. You might be wondering, how does that actually translate in the real world? How do they measure performance in something like Cutlass? Great question. They compare the performance of operations using various data types and assess how close they come to the theoretical peak performance of the hardware. For instance, when running GEM on a Blackwell architecture GPU, Cutlass can achieve nearly optimal throughput rates. It's like scoring a touchdown in every play of a football game. Before we wrap up, I want to touch briefly on something called Qt, introduced in Cutlass 3.0. It's quite innovative. Qt abstracts the complexity of working with tensors and layouts, so developers can focus on the logic of their code. That sounds like it would save a lot of time. Are there any usage examples? Definitely. There are plenty of examples showing how to implement various computations. For instance, basic GEM operations with minimal code changes from prior versions, or even advanced implementations for neural network layers in deep learning applications. To summarize today's discussion, Cutlass is all about optimizing high-performance computing on NVIDIA GPUs with an impressive amount of flexibility and efficiency. The new features in version 3.8, particularly with Blackwell architecture support, enhance its already robust capabilities. If you're